Cool. Welcome everybody. Now that we got a couple more people in here, we'll go ahead and get started so no one's left out. My name is John. I work with GoEngineer. I'm an applications engineer, but of course you could probably read that from my screen. And this is my email if you want to contact me afterwards. And today this webinar is going to be covering all of the, well, not all of the features, but some of the really cool features I wanted to show you guys when you upgrade from Simulation Standard to Simulation Professional. Upgrading from Simulation to Sim Pro gets you a couple of extra options. These are the kind of additive things after we go from Simulation Professional. So those who have Standard are probably well familiar with the static assemblies. They're probably, you guys probably have gone through fatigue, motion analyses. You can kind of, you can move things from one spot to another, get contacts understood so that you can run that snapshot in a static assembly or static study. And hotspot detection, that's a very commonly used tool because we need to make sure that our meshes are really good, and if you don't have really good meshes understood in Simulation Standard, those are skills that definitely pour over into Simulation Professional in the higher levels. All right, I'm just going to open this up just to keep an eye on the questions in chat. Looks like everyone's good. Cool. Sweet. So today I am going to be picking out 3 topics out of Simulation Professional. The main topics that we'll be taking home is going to be the parametric study. And one of the really nice things about that is that we can import results from other analyses. For today, I'm going to be running a frequency analysis. And then we'll use basically how sophisticated or the results of that result of that study. We're going to throw that in our parametric study. And I'm also going to go over drop testing because it pertains to the model and the type of analysis that I'd like to run today. And the better view of our itinerary, saying that 3 times fast, I start with guitar strings because waves on a string behave very nicely with input frequencies. It's a great way to show how a model is just excited with a lot of different frequencies and how we can sweep for normal modes. After that, we will be investigating a case study where we have a drone and we want to test how strong it is, see how it compares to a static study. And after that, we will run a frequency analysis because there are motors on the drone. They last I looked up, they average resonance around like 5,000 hertz. So if we have our product that is going to resonate at a certain frequency, we want to make sure that the model isn't going to resonate at that frequency so it doesn't fall apart. And then we'll optimize the analysis to see if we can change anything in the study geometrically. So cool. The first case study, for those fellow guitar players or music nerds, we will be doing a sweep of frequencies across the set of strings that are actually as close as I could get to a baritone guitar. So it starts from low B, goes through regular E tunings, and then it goes up to a couple other higher notes, just so it just works nicely for if you guys are interested. It's called perfect fourths or fourths tuning. It's kind of how a bass player will tune their 6-string basses, and then you just adapt it to a guitar string. It's a great analysis for us to show how the basic fundamentals of a frequency analysis. And of course, why do we care about frequencies? Well, if you guys remember your physics class, or if you had any vibrational analyses classes, you may run into the principle of superposition, which states that if you have any number of waves can be stacked on top of each other and they can be equated to one wave, you need a fast Fourier transform, obviously, to do that. And how it works with engineering is if we have a force going into an object, some of it goes out of the other end, and some of it stays inside the object, gets reflected back into the material. And if you have an oscillation occurring in your part, that's just going to keep that force like basically going back and forth between whatever boundaries your parts exist in. So unfortunately, some vibrations are just not going to help us make a productive design, and they can actually break a lot of our models. So without further ado, let us go into SOLIDWORKS and show you guys all the good stuff. And for today, sorry, just move this across here. In Simulation Pro, starting any new study, it's up at the top left here. Just going to show you guys the basic clicks of starting a frequency analysis. This one is already solved because I don't want you guys to sit here waiting for this to solve. So basically frequency, I have Simulation Pro activated, and I'm just getting a little bit ahead of myself. If you need to access the higher levels of simulation, there is in the add-ins the SOLIDWORKS simulation button, and I have Simulation Professional turned on right here. So frequency analyses. At the top of the window we have our frequencies, basic study tree. In the properties window, this is where we do a lot of our fine-tuning. I said for this guy, okay, I want to sweep the strings for 58 frequencies and see how they behave. Similar to a simulation standard, there is fixtures, and this was a reference geometry. I kind of try to approximate how you would fix the string similar to how you'd do it in a simulation. And the tension, these guys are being pulled, obviously, but this is also just a fixture. And these individual newtons that you can see here, this is approximately what I thought, or what I tried to calculate, just really basic calculations of each string's individual tension, so we can hold a certain note when you pluck the string. And that's all pretty much covered in Sim Standard, but the results, one of the greatest thing that I like about this is the right-clicking the results folder, and you list the resonant frequencies. Here we can observe where our what resonant frequencies exist in our model, and I know that there's a lot of like destructiveness in frequency analyses, but since these are waves in a string, they tend to behave really nicely and exhibit lots of resonant frequencies because that's just kind of their job. Of course, you need a lot of energy to destroy things with waves. I'm sure you guys have seen that wavy bridge, right? Resonance. That's kind of the best example that we have. And we can also define a specific mode shape that we want to view. We can see a frequency response graph. And I'm just going to use one of these pre-made results. It's going to right-click it and edit the definition, so we can just see what the features are inside each one of these guys. Apologies, I'm getting just a little bit of lag. I'm also going to check the questions. Is there a difference between Simulation Pro and Premium? Yes. The biggest difference that I like to point out is the materials. Your dynamic analyses, they take into account your stress strain curve after your linear stresses. So Simulation Pro still lives in that linear world. So if your studies, or if you ever run into an issue where you have to turn on or say no to large displacements or say yes to large displacements, that's what Simulation Pro lives in. The limitation of Simulation Pro is that dynamic elasticity kind of analyses. After a certain point, the material can yield really weird results, but if you change your deformation scale to true scale and you turn off the large displacement flag, you can get pretty accurate results, enough to at least proceed on with your analysis. So here it doesn't look too much different from Sim Standard. Obviously, we can change the fringe mode, right? That's all nice. But let me at least show you guys what the frequency analysis looks like. And you just go, you can either double click it or you can right click it and show. And again, this is all just covering the basics so that when we apply this to the drone model, then we can kind of go through it a little bit quicker. Cool. So we have our just one sine wave. We can animate it so that we can see kind of how it exhibits its behavior, but it is an exaggeration because SOLIDWORKS has a deformation scale so that we can better understand what's going on. And if you guys have actually recorded guitar strings, you'll note that the frame rate can change how you view the oscillations. So SOLIDWORKS is a really great way to kind of avoid some of those errors in how we translate one observable kind of phenomenon through another type of measuring medium. So I hope that's wiggling for you guys. I'm just experiencing a little bit of lag because I think I have my main drone analysis is a pretty big one. I'm going to open up the questions just once. It's possible to enlarge my screen by removing an image, maximize the SOLIDWORKS screen. I am not sure. That may be just depending on your oh yeah, let me remove my webcam. As much as I enjoy the background, it does cost us bandwidth. So cool. All right, I hope you guys can see that really well. I can see it now. The oscillation of the string. We'll just go and view a couple more, or just one more. Then we can move on to the drop test. And I think the chat box, if you pull out the orange triangle, it's like one of the lower options. It just says chat, but the Q&A is fine. I can see when you guys put in a question there. So this is cool. We can observe the different normal modes within an analysis. Awesome. And we can see how that behaves. Obviously, yes, it is a little bit exaggerated because the string would never stretch this much, obviously. But it does exhibit these characteristics. These waves do happen if you just pluck a string. And in a future example, I probably would incorporate boundaries so that we can emulate what frets would do. But that's probably going to be for a whole nother content piece. So cool. Any other questions before we move on? What are the units on the displacement? Amperes, this is... I think this is just in hertz, but we can check that by editing the definition to see exactly what it is. Because right now it's just saying the mode shape is 10, the value is at 8 hertz, so this is kind of showing the displacement in amperes. But let me get that amplitude shown for you. Yeah, it looks like this is just unitless. Plot step hertz. Yeah, amplitude's unitless, so it's kind of like a percentage. You can think of it that way. Well, cool. All right, with that, we are going to proceed to the next example. All right. So the next part, drone drop testing. How it differs from static studies. Static studies are kind of dependent on having a model fixed somehow. And I have never seen an example where we have drones fixed to things and then flying. Usually they're propelled by propellers, giving them lift, obviously. And I thought this was a really good example to show how you can actually translate a dropping motion and see how the forces work in that way. You technically could run a static study, but you are also going to be fixing the model in certain places. So you may observe stresses at places where you're just fixing the model, where it may not actually really have any effect to the end model. After that, we're going to run the frequency analysis, and you can see these purple triangles at each corner. I included those so that they can emulate how much weight would be there with each motor. Kind of gives it some dampening as well, so we can kind of give some of the normal modes to die out. And this is our optimization study. This will be our end goal. And you can note we have frequency in here and frequency in there. I will get into that later because there are ways we can subdivide that. Constraints, goals, variables. Cool. So the drop test. Drop test covers falling in the direction pointing towards gravity. You can also give it an initial velocity, so it's not just dropping, it's kind of approaching a wall or a surface that's like a square, a perfect plane. You can do both, and I will show us both. And if you didn't want to make it a perfect rigid wall, say it wasn't made out of concrete, you can put dampening coefficients in there. There we go. Cool. All right, and this is the main part that we'll be working on. I'm just going to quickly show the entire assembly, and then I'm just going to close it out because it is costing me quite a lot of resources to just show this, but it's also the broadcasting, of course. So this is the basic drone base model. It's really a great idea. In Sim Standard they talk about this, that you need to simplify your model, because when you mesh things, you can overdefine the mesh. Oh, did it decide to? Okay, it decided to go away. All right then, no worries. So this is a simplified model. You can see these coordinate systems right here. I made these because I applied what's called a remote load. So what a remote load says is you don't need the geometric data, you just need the weight, center of mass, and you can input that and have a dummy load set on your model so that it's essentially doing the work that would be there if the model was actually there and you ran the analysis with it without costing extra computational resources. And that's just a tip. You can do that with any study, really. So cool, we'll open up the drop test, and it looks like unfortunately the results may have to be rerun, so you just have to take my word for it, but the drop test parameters right here, let me just open up the setup. You can see I have the right plane highlighted, and this red triangle designates which direction gravity is facing. You can have it face obviously normal to the I think top plane if you have it falling straight down, but this is one way that you can say that, okay, this is falling in this direction with from a height of 10 meters. You can change the units to whatever you'd like though. And the target is normal to gravity or parallel to the reference plane. That's just telling you how you want it to fall. And there is our contact dampening. So if we want to say that the wall isn't perfectly rigid, there is some give to it, this is where you add a dampening coefficient. And the dampening coefficient says like how much percentage is conserved through the rest of it. Next, I'll just show the force equivalent, that you don't need just a dropping height, you can just give it a velocity. And it looks like we got another question. What output can we get in the drop test? It's essentially, so we have stress, displacement, and right here I'm just going to define a stress plot. Unfortunately, I did run the analysis, but after you run the design study, since I pulled some things out of there and the model has changed because I ran that design study, the results no longer, they have to be rerun, unfortunately. So I'm just going to show you guys just the options. So here we can make a von Mises stress, just the stress over the entire model. We can do stresses in XYZ, principal stress, all that great stuff. Another tidbit is you can pull the list stresses, displacements, and interaction friction forces. And what this will help us show is at the instance that it interacts with our wall, it'll give us what resultant forces went through that model. And again, my study results have to be rerun, but again, I don't want to rerun the study just to have you guys sit here and watch a loading screen. So it's essentially working backwards from a static study. It's saying, okay, from this height or this velocity, it hits this boundary, exerts this force through the object, and then we can kind of pull different results out of that. Right, I'm just going through the questions really quick. Oh, they're not. Oh, the chat box isn't allowed in the. I'm not sure, but this the questions will work fine, and I hope I didn't answer that question late. Great. Okay. Cool. All right. So unfortunately, I'm sorry that I could not show the actual animation of the drop tests without rerunning this. But without further ado, it is not the biggest deal because the real meat and potatoes is coming. And we are now at the frequency analysis. One of my favorite things about this. Sorry, I saw another question pop up. Units of displacement. Oh, units of displacement. If you meant that for the drop test, that can be in millimeters, that can be in inches, basically whatever you wanted to. There's a lot of options that you can put them in, so whatever you'd like, really. I think in the previous example, I had them in millimeters. So cool. Moving through to the frequency analyses, basically the same as the string analysis. However, now that we are working with an actual model, this will actually show us where the resonant frequencies are, and since this is not a string, it doesn't behave as ideally as a string would. This is where we get into destructive, well, I guess technically constructive interference, but in a very destructive manner, because the waves are getting stronger, so to speak, or they're at least resonating to break things, break the bonds of our model, which we definitely do not want. And this is one of the results that we will be able to observe, just one of the normal modes. It does look interesting, and the deformation scale is scaled pretty down, but since we're in the linear environment, our true scale results will be very abstract, so to speak. Cool. And again, I want to show you where we can access these analyses types. Drop test, frequency, and design studies are all available once you activate your Simulation Pro license. Nonlinear and linear dynamic are not allowed, and submodeling, they're not allowed in Pro. They are only in, actually, submodeling is, but nonlinear and linear dynamic, those are in premium. And that's where we get to much more beyond linear phenomenon with our models. So great. So yeah, well, let's open the frequency analysis, and I'll be able to show you guys the basic setup for it. It's actually relatively very simple. I didn't need to add these remote load masses, but you do need to incorporate gravity. Since in contrast to a static study, this is not using any fixtures, I'm going to right click the frequency analysis and show you guys a really great option if you just need to run an analysis in empty space. We have the use soft spring to stabilize model, which is fantastic because I can say that this is technically just existing in this computational space, and we want to excite the model with 30 frequencies and have that spread around 5,000 hertz. Because again, the motors on average oscillate, or they have a resonance at 5,000, so we want to make sure that it's structurally stable at 5,000 and hopefully minimize the resonant frequency of the model. Material properties from 3D printing like FDM. Yeah, there are, and you can add your own. So really quickly, if you go to apply edit material, basically go to your model, right click, apply edit material, and if you have to add your own parts to it or your own materials, there is a custom materials at the bottom of the list of all of the standard materials. This one is ABS EV Eric Vega, who used to work with us. He was kind enough to offer this model for me to use and for me to run the study on. And this is where you can input all of your materials as well. And like I said before, the limitation of Pro is these linear, elastic, isotropic, and orthopedic. That is just the limitation of it, but luckily we can do a lot of really great things with that. And side note, to further aside for that answer, if you have two custom materials folders, you may need to check which file location you're at just by hovering over it, because if you have one that is in program data, I think program data files, I gotta move this one. If you move all of that data to another computer or you reset that computer, you'll lose all that, so you just got to move it to another folder. But this is where you can apply either standard, what SOLIDWORKS has provided for our plastics, or you can input your own materials that way. So great. We have our load masses that kind of takes care of some of the dampening. Similar to a real-world example, gravity exists, and this particular example really didn't. It can't be run without it, and so we have to incorporate gravity in the external loads. We have our gravity, remote load mass. I'm just going to open it to show you guys because I think it's a fantastic tool to save on resources and to get as close as we can to reality, right? So if we just apply a rigid connection with mass, I selected the faces where it would be attached to, where the bolts would exist. You do have to create a coordinate system, which you can create a sketch and then search for your coordinate systems in the top right of the search bar. Call that dot a coordinate system, and then you can use that for your remote load mass. Got another question coming in. Can we analyze fracture phenomenon in the model is 3 types of crack propagation? Crack propagation would be the best done in fatigue analyses, actually. But we can do that with a drop test, where you would be able to observe, and luckily fatigue is offered in standard, and I'll show you where our YouTube channel is because we do have content on that. Yeah, fatigue analysis would be the best one for that. Of course, here it would be the stress, where we have our stresses, right? But over fatigue, you can do that over a certain number of cycles. And I'll hold that till the end of the class so that I'll just show you the website so you can see that piece of content. Similarly to the guitar strings, we have our list of resonant frequencies. And if you have a pencil or paper, or let's be real, we're all engineers, we're pretty good with numbers. We can observe that 4,981 is our kind of our closest to 5,000. but it's close enough that we can maybe trust actually 5,000 hertz. But luckily we have a little bit of variance going up to 5,322 hertz. So if I start my optimization study at saying that, okay, we already know that we can allow 5,000 to 5,300 hertz to exist in this resonant frequency, we still want to minimize all of our resonance within our model, and we're going to click on certain parameters to change with that. So cool. Before I move on to optimization, does anybody have any questions on this? I'll give it a second. You guys have been really great with throwing in questions. I'm really enjoying it. The more impromptu live feel, as if we were in person. Cool. All right, well, I'll move on. Of course, if you have any more questions, just keep them coming. So, last and certainly not least, we are here at optimization. My favorite thing, because you can run multiple scenarios depending on the allotted variables that you allow to run. So what I mean by that is, say we have we pick our first dimension, and we say that can vary with, we want it to range from this number to this number in this number of steps, and SolidWorks will calculate, oh, okay, you want to run this number of scenarios. It kind of makes a cross matrix of the possible combinations of what's possible in our analysis. Red, you guys could probably infer, means a failed scenario. White, I have it highlighted in black, sorry about that, is a pass, and optimal is green. Optimal hits as closest to your goals as you want it to. And you can get extremely restrictive with this study. For this example, this picture right here, I thought it was going to fail. I gave, if you see the frequency right here, I only allowed it to resonate, this is like a given, I only allowed it to resonate at 4,950 hertz, only up to 5,070. So basically only like 120 hertz with variance, and it still found an optimal output. Also, side note, since we ran the frequency analysis, if we change the definition, basically the number of frequencies we sweep in that analysis, then we will affect the number of frequencies available to the optimization study to solve through. And I will show that later. That was actually something I discovered while putting this presentation together. You could say I learned it the hard way, but it was very fascinating because it made me really appreciate how sophisticated referencing your previous studies are, so that you don't have to rerun anything. It basically just says, oh, you want to reference the study you've already run, kind of referencing those results. So great. This is what it looks like when it's all done. Unfortunately, setting up a new one, I've already done it right here, but I don't only want to go so far, so I can still show you guys the results, because it will change things. But I have another design study. Whoops, clicked on drop test. I have another design study that I can show you all the picks and clicks, because it's actually relatively simple to start this. Sorry, let me get this window. There we go. Need to change the cursor box that we got. So cool. Setting up the variables. I'm going to show you guys the parameter. When you add parameter, it is going to open up all of the dimensions in your model. And I'm going to zoom in to one leg. And of course, if I were to, the next time I do this, I will probably run this as a symmetry study. So I only have one leg to actually focus on. But for the purposes of this analysis, I just like showing the rest of the model. So I chose leg thickness. That is this dimension right here. And if you can see my cursor, it has an actual dimension icon. We are literally going through the model and saying, okay, this dimension, that's this value right here. I want to take that leg thickness down here, say that, yeah, its minimum can be 0.13 inches, and at maximum it can be 0.45 inches. So I'm basically saying, well, I'm saying that leg is going to either be, there's like a support right here. I don't know, you guys can't see my screen or my webcam anymore, but there's a support right in here. Let me slowly pan this over. There's a support underneath this guy right here. And the thicker it is, I just really wanted to test, like, how does this thickness really change the resonant frequencies. The second one, if I can just pan this back over, gap is this opening right here. Because when we observe the resonant frequencies, we can see there's a lot of movement in this leg right here. So I chose that guy. It's a little hard to see, I apologize. There are a lot of dimensions in this, so I had to do a reasonable amount of interrogation to find the right dimension to click on. So after that, we can say that yes, at minimum we want this to be at 0.01125 inches, at maximum 0.03375, and our steps are in 0.05 inches. And you can see the active number of scenarios. It is taking your step, subtracting that from the difference between your minimum and maximum, and then spitting out how many scenarios can possibly exist within those two axioms, right? Or those two range values. And of course you have your minimum and maximum value added to that. So the difference between your minimum and maximum divided by 0.05 plus your initial and end. Constraints. Constraints is made through the sensors. So if you want to probe a particular point on your model, you can just choose a vertex. You can choose a face. For this one, if we go to simulation data, this is one way we can say that we want to look at the frequency, strain, whatever. And I like to think about constraints as if you're saying, okay, this exists in the model. This is what we need to allow it happen. So and if you remember the results of our frequency analysis, I was just able to include 5,000 hertz, and I cut it short at 5,250 hertz. Excuse me, and that's kind of the allowed range that this is allowed to resonate at. And our goals, obviously, are running our mass because it's a drone, it's flying. The more energy it costs to get it off the air or off the ground, that's just more voltage we're losing, so it flies for less time. So we want to minimize that weight. And the actual value weight right here, that just says how important that parameter is, that goal is. The reason why it's weight 5 on the frequency is because I wanted to minimize the resonant frequency as much as possible, and the weight, luckily it's still sitting at 0.3 pounds. It didn't really change much in the analysis, so I just said keep that at 1, lesser priority because it's not changing anyways. With, you know, what's the difference in weight between 0.011 inches and 0.033 inches? Not much. So the frequency was really what I was getting at. And this box right here, it pulls out a little window. And if we ran a drop test frequency analysis, I actually don't know how that would happen, but we can input that to minimize the frequency. But utilizing the actual frequency data from our frequency analysis, we have that option available right there. Nice. And now I'll open up my finished study, go to the results, and here I would like to note when you click on optimal, it will update the model to show you that optimal view. And if we wanted to run another analysis off of that, all you have to do is right-click Design Study 2, the name of the title, and you create a new study off of that, and it'll take that model and now run that study with that updated model. For frequency 1, it looks like I did change it to 4,900 hertz to 5,100 hertz. And it looks like we have 3 scenarios that actually worked. We had one that was allowed to resonate at 4,900 and 5,000. And the optimal study gave us the best minimized resonant frequency at 2,360. So now we can safely say, yeah, we're allowed to have 5,000 hertz oscillate on this, but it's not going to destroy the drone as it's flying from one destination to the next, whatever it may be doing, atmospheric measuring, or if it's getting a really cool shot of a snowboarder going down a hill, or a skier, what have you, snow sports, doing something awesome. Drones are great for that. So great. We have covered frequency analysis and how we can throw that data into our optimization study. And we just went over drop tests, and again, I apologize that the results did not want to cooperate after I ran the drop test, or after I ran my design study yesterday. But that concludes the webinar, honestly. And if you guys have any more questions, I'll be here for a little bit longer. And yeah, if you guys have any more questions, let me yeah, go ahead and throw them in the chat. Sorry, I just repeated myself. Let me also show you where you can find our YouTube channel, because I know you, who was it? One of you guys were asking about fractures. Just trying to pull that up so I can get your name. Varun, yeah, or Varun. I hope I'm pronouncing your name all right. I apologize if I'm butchering it. But yeah, fracturing phenomenon, that will be in fatigue. So if you go to YouTube, go to GoEngineer. And here is our YouTube channel. And if you go into the search, got to remember how to spell it. Fatigue analysis. We have quite a few videos on that. So that'll help you set up your study so that you can run, you can import like a static study and run that over n number of cycles and see how that affects your model. And then you'll be able to observe your fracture data. Yeah. Any other questions for today? If not, you guys are free to go. And yeah, again, we have, where did that go? We have our YouTube channel, of course. We also do offer training on our website, and you can sign up for our newsletter. And if you wanted my email one more time, you can always email me questions. You can always set up an appointment so we can go over whatever tools you'd like to learn, so you can apply them to your products. And you can choose any one number of application engineers, not just me, to help you with your design, depending on whose expertise is really perfect for you guys. Thank you for watching. Don't forget to hit that like button and subscribe, and if you hit the bell notification, you'll be notified when we upload new content to the GoEngineer channel, your #1 resource in SOLIDWORKS engineering. Thank you.